Okay, so in these few exercises, we have to decide whether the given function is even or odd or neither even nor odd. So the first one is this constant function 3. First of all, we have to see what its natural domain is. The domain of f in this case clearly is the entire set of real numbers. For every x belonging to the domain we have f of minus x. Note that for any real number x minus x is also a real number. So f of minus x makes sense. We can evaluate f at minus x. So that is also equal to 3. So this is equal to f of x. Hence f is even. Here we are not explicitly mentioning that minus x also belongs to the domain. You can see that is the case. So this is an even function. Then 28. F of x equal to x to the power minus 5, or in other words 1 divided by x to the power 5. So in this case the domain of f is we can put every real number except 0 because we have x to the power 5 in the denominator in this expression for the function. If you write it as 1 over x to the power 5, that is. So the domain is the set of real numbers from which 0 has been removed. Now for any x belonging to the domain, note that minus x also belongs to the domain. That also this time also we are not mentioning that, because you see, since x is a real number different from 0, so minus x is also going to be a real number different from 0. Now what happens if we calculate f of minus x? F of minus x is minus x whole to the power minus 5, because 5 is odd, so this will be minus of x to the power minus 5, which is equal to minus f of x. Hence f is odd. Then 29. Square plus 1. In this case, the entire set of real number is the domain for any x belonging to the domain we have f of minus x equal to, so you can see that this is going to be an even function. Hence f is even. I think I am already running out of ink. Third, f of x equal to x square plus x. In this case, also you can put any real number and get a real value, unique real value for the function as the functional value. So the domain of f is the entire set of real numbers. But here we will see that it's not an even function. It's neither even nor odd. Note that I think we can take one will work. 1 belongs to R such that f of minus 1 also belongs to the domain, that is fine. But now what is f of minus 1? F of minus 1 is minus 1 whole square plus 1, plus minus 1. So this is 0, whereas f of 1 of course is 1 square plus 1, that is 2. So we see that f of minus 1 is not equal to f of 1. Clearly they are not equal. Also they are not minuses of each other, since f of minus 1 is not equal to f of 1 and at the same time f of minus 1 is also not equal to minus of f of 1. F is neither even nor odd. Then 31 gx equal to x cube plus x. This will be odd. The domain of G, or the natural domain of G, is the entire set of real numbers. For any x belonging to the domain, we have g of minus x equal to minus x whole cube plus minus x. So this is minus x cube, because 3 is odd, minus x, and that is equal to minus of x cube plus x minus g of x. Hence G is odd. X to the power 4 plus 3x square minus 1. You can, looking at the formula for the function itself, you can pretty much guess what the function is going to be. If you see even exponents 2, 4, 6, etc., then the function is likely going to be even. Of course, you can only say that after you have verified that the function is even, but you can guess beforehand that the function is, this function for example is even. Here we have odd exponents 1 and 3, so it's odd. But here we have mixed exponents 2 and 1, so it is neither even nor odd. You can guess like that. I mean, at least for the functions that we see, which are polynomial functions, that is where the formula is a polynomial in x. The domain of G is R. For any x belonging to R, we have g of minus x and this is nothing but g of x Hence G is given. Then 33. One over x squared minus 1. Don't forget to first of all find the natural domain, because even before you verify whether the functional values at minus x and x are this and that, you have to make sure that it makes sense to evaluate the function at minus x. That is, for every x in the domain, minus x also is again an element or a point in the domain. If that itself is not true, then of course there is no, it does not make sense to ask whether the function is even or odd. It is not neither even nor odd. In that case, if that happens, we haven't seen that so far in any of these exercises. Here the domain will have all the real numbers for which x square minus 1 is not equal to 0. Now there are two such real numbers for which the denominator is 0, minus 1 and 1. So we have to remove them from the set of real numbers. That will be the domain. And the way we are writing this sentence, it has to be interpreted under the condition that for us domain means natural domain, the largest possible domain that can be taken. If we just simply write this sentence is not entirely mathematically true. If we are given a functional, a formula for a function like this, it actually is meaningless. A function must always come with a domain. Then only we can say it's a function. However, the way we are dealing with these things, we have made the convention that when we are given a formula like this, then there is a largest possible domain that can be taken, that is the natural domain. That's what we mean when we write the domain of G is this. Okay. Minus 1 and plus 1 have been removed. Now, is it true that if we take x in R, then minus x also is in R? Let us see. Since that is not obvious, we have to write something here. Let x belong to R minus this, then x is in R x is not equal to minus 1 and x is also not equal to 1. This implies minus x belongs to R, which is coming directly from this. Minus x is not equal to 1. This implies this, and minus x is not equal to minus 1. This implies this. and hence minus x also belongs to this. Now after ascertaining that for every x in this set minus x is also in the set, now it makes sense to ask whether G is even or odd. For any x belonging to we now have G of minus x. Now there is no danger in writing this thing because minus x also belongs to the domain of G, so G of minus x makes sense, and this is going to be, again you see, because even exponent is involved, so the function is, you can guess it will be even, and in fact that is the case. This is equal to G of x, hence G is even. Then 34. Our guess that when mixed exponents are there, the function is neither even nor odd, that case will not work here. That's why I said that your guess only works when the formula for the function is a polynomial. This is not a polynomial, it's a quotient of two polynomial expressions, x and x square minus 1. Individually they are polynomials, but the quotient is not a polynomial. Anyway, we will see. Here also we don't have, as far as the domain is concerned, we don't have to worry about the numerator. We worry only about the denominator. We want it to not be 0. So the domain of G is again of course, because we are solving a set of exercises, I am able to write like this. If you have only this exercise, you cannot write this part. You have to include this here. In the solution to the previous exercise, that for any x belonging to this set, we have minus x also belonging to the set. Okay, now what happens if we calculate g of minus x? Minus x divided by minus x square minus 1. It is minus 1, no? Yes, okay. So this is minus x divided by x square minus 1. We have taken this minus outside, which we can do, and this is equal to, now this expression is nothing but g of x, so minus g of x. So g of minus x is minus g of x, hence g is odd. $35. H of t equal to 1 over t minus 1. So this exercise is a case in which that criterion that every element, for every element in the domain, its negative also belongs to the domain, that itself will fail. That is not true. The domain of H is, the denominator should not be 0, that means t can be anything but anything other than 1 or minus 1. Note that the point minus 1 belongs to our domain, but minus of minus 1, which is 1, does not belong to the domain. The consequence of this is that B cannot, oh sorry, this is not G. B can calculate H minus 1. There is no problem in that. But we cannot calculate H1. So, since we cannot calculate H1, it is meaningless to ask whether this is equal to H1 or this is equal to minus h of 1, and hence that is because h of 1 does not exist or is undefined. So that's why this function is neither even nor odd. the definition of evenness and oddness does not apply to this function. So that also is, in that case also we say it's neither even nor odd. So H is neither even nor odd. Then 36. H of t equal to t cube, but not just t cube, the absolute value of t cube. Because of that absolute value, it will be even in spite of having an odd exponent here. Note that this is not a polynomial function. So we start with the domain. Here there is no restriction in taking t. T can be any real number. The domain of H is the full set of real numbers. We have, because we are, it does not matter if we take x also, but just for the sake of beauty, let us take t. We have h of minus t. Since we already know that for every real number t, minus t is also a real number, so we are not mentioning that part. We are directly calculating h of minus t. Because of odd exponent, we do have minus t cube, but because of the presence of modulus function, absolute value function, minus t cube, mod minus t cube is equal to mod t cube, which is h of t. Hence h is even. Two more are there in this type of exercises. The next one is h of t equal to 2t plus 1. The domain of H is R. Okay. The domain of H is R. This is going to be neither even nor odd. But what value will help us show that? Minus 1. If we calculate minus 1, then we get minus 1. We take 1, yes. Note that 1 belongs to R such that so this is minus 2 plus 1 minus 1, and h of 1 of course is going to be 3, since h of minus 1 is not equal to h of 1, and at the same time h of minus 1 is also not equal to minus h of 1. H is neither even nor odd. If you are wondering how one can guess beforehand, I mean before writing the solution, whether the function is even or odd, and accordingly whether to write this type of solution or the other type, the answer is you have seen these solutions, so you study them carefully. From that itself, from that much experience with this type of things, you will be able to decide for yourself what is to be done if a new function is given to you. And finally, exercise 38. This is going to be even. For any t belonging to the domain we have h of minus t equal to 2 times absolute value of minus t plus 1, which is 2 times absolute value of t plus 1. Don't make the mistake of writing this equal to 2t plus 1. If you forget to put the absolute value, then that's a mistake. This is not equal to t. This is not always true. Some people will make this mistake. They will think that since there is minus, we have removed the minus, so it will be t. No, that is not the case. The values for which this will be false are the negative values. For example, if you take, in place of t, suppose you take minus 1, then what will this be? 1. However, your t is minus 1. Is 1 equal to minus 1? No. So that's why this is not always true. And this is nothing but h of t. Hence, h is even. Okay, so these are even and odd functions. Next we go to sums differences products and quotients of functions. Now some exactly 4 exercises are given here under this type of exercises, but unfortunately okay, let us see the exercises, then I will say what the issue is. In exercises 39 and 40, find the domains and ranges of f, g, f plus g and f dot g. So in the 39th one, the function fx is the identity function which maps every element to itself, every real number to itself, and gx is square root of x minus 1. Without thinking of any issue or whatever, we straight away start solving this, and then we will encounter a problem. There are some things which we can immediately say. For example, the domain of f, of course, is the entire set of real numbers. The range of f is also the entire set of real numbers. Because the function is so easy, what is domain? Domain is the set of all possible inputs, and range is the set of all possible outputs. So you can put any real number here, so the domain is R, and also any real number will appear as an output of this function for some input. So the range is also R. What about G? Domain of G, you cannot put any real x here. X minus 1 needs to be non-negative, greater than or equal to 0. So that means x must be greater than or equal to 1. We should have this in order for g of x to be a real number. So equivalently, x must be greater than or equal to 1. So any real number greater than or equal to 1 is allowed. So in this case, the domain is this interval, closed ray, starting from 1 and going towards infinity, plus infinity. Okay, so domain of G is this, and range of G, Now what type of outputs are these? Whatever they are non-negative. I mean, you cannot have a negative output here, because this by definition is the positive square root of something, namely x minus 1. I should not say positive but non-negative, because you do get 0. When x is 1, when you put the smallest possible value of x from the domain, then the output is 0. So you do get 0, but then you get positive. So we can say that the range is contained in the set of all non-negative real numbers. But the question is, will every non-negative real number also be in the range? That is, if you arbitrarily take a non-negative real number, is there an input for which this chosen number is the output under the function? Because then that chosen real number will belong to the range, since it then becomes an output. So now we are going to show that that is the case. So let y belong to 0, infinity. There is not going to be much problem in showing this. We want an x here such that g of x, that is, this becomes equal to y. So you solve for x square should be equal to y square minus 1. Oh, sorry, what the hell am I writing? X minus 1. X minus 1. So that means y square plus 1. Okay. So our x should be y square plus 1. Then y square plus 1 belongs to 1, infinity such that g of y square plus 1 Now there are a number of things to be noted here. First of all, how are we claiming that y square plus 1 belongs to 1, infinity? For that to happen, y square plus 1 has to be greater than or equal to 1. Is that the case? Yes. Why? Because we know that since y is a real number, y square is non-negative. So you add 1 on both sides. So y square plus 1 becomes a real number, that is at least 1. It can be more than 1 also. So it belongs to, this means it belongs to the domain of G. So when we evaluate G at this point, that is meaningful. If you try to evaluate a function at a point that is not in the domain, then that does not mean anything. That cannot be done. Okay. Now when we are actually calculating this, fine, you have put y square plus 1 minus 1, so 1 and minus 1 cancel out. So you now have absolute, square root of y square. Now is this equal to this? This is not always true. This is true only when y is greater than or equal to 0. Fortunately, that is the case. Because y has been chosen from here, so y is non-negative, so we are getting y. Now what does this mean? It means that y is appearing as an output for this input. This implies y belongs to the range of G. So any element in this interval belongs to the range of G. Hence, this interval is a subset of the range of G. Now combine these two inclusions. So range of G is equal to this. Now the issue that I was talking about, that thing appears when one tries to find the ranges of f plus g and f dot g. We will see. Let us now go to that part. Next, we have in this case also we can readily write the domains. We already know what these domains are. They are equal to the domain of f and the domain of G intersected. It makes sense also, because if you want to calculate f plus g, then by definition f plus g at x is f of x plus g of x. For this to be meaningful, x must belong to the domain of f, and for this to be meaningful, x must belong to the domain of G at the same time. So x must belong to the domain of f and domain of G. So it must belong to their intersection. And conversely, for any x in this intersection, these two things make sense. So this can be calculated, and that's why the domain of both f plus g and f dot g, because of that same reason, f dot g is this. So both the domains are this intersection. So which is what? One of them is the domain of f is R, this is the larger one, and the domain of G is this. So the intersection is 1 comma infinity. Okay. Now we show that the range of f plus g is also equal to this ray 1 comma infinity, and the range of f dot g, this will be equal to 0 comma infinity. Now the problem is this. Let me write the solution and then I will say. For any x in 1 comma infinity, that is the domain of f plus g and also the domain of f dot g. Have we dealt with f dot g? First we are dealing with f plus, okay, so we will see that multiplication afterwards. So we are choosing any point in the domain of f plus g. So let us now calculate f plus g at this point and let's see what the output looks like. We have f plus g of x equal to f of x plus g of x, and that is equal to x plus square root of x minus 1. Now note that this thing is greater than or equal to x, because square root of x minus 1 is greater than or equal to 0. So if we remove it, then either it will remain the same, which will happen when this is 0, or when this is positive, its removal will reduce the value. So we will have x, and x, because we have chosen x from here, x is greater than or equal to 1. So we see that whatever point we choose in the domain, the output for any input, the output is greater than or equal to 1. This shows that the range of f plus g, which is the set of all outputs, is contained in this interval, because all outputs are greater than or equal to 1. Now the converse. Now let y1 be any point in this set. If y1 is equal to 1, then f plus g of 1. If y1 is 1, then that appears as an output for the input 1 under the function f plus g. So we now assume y1 greater than 1. What is our aim now? Our aim now is to prove that the reverse inclusion is also true. Namely, this set is also a subset of this. So we have arbitrarily chosen an element in this set. We want to prove that this y1 belongs to the range, that is y1 is an output. In the particular case where y1 is 1, it is an output for the input 1. So now we assume the the other remaining cases where y1 is greater than 1. Okay. Since f plus g of 1 is equal to 1, this we have already seen, this is less than y1, which is less than y1 plus 1 plus square root of y1. And this is, if you look carefully, f plus g of y1 plus 1. There is no problem with this. 1 is less than y1, that comes from our assumption, and y1 is less than this because 1 plus this is already greater than or equal to 1. So in particular it's greater than 0, strictly greater than 0. So the second inequality is also true, and this is equal to the f plus g image of y1 plus 1. Since y1 belongs to 1, so y1 plus 1 also, belongs to 1 means belongs to this interval. So y1 plus 1 also belongs to this interval, and this interval is the domain of f plus g. So it makes sense to calculate f plus g at y1 plus 1. But the question is, why are we writing these inequalities? Since this and f plus g is continuous on 1 comma y1 plus 1. See section 1.5. We have y1 is equal to f plus g of x1 for some x1 belonging to by the intermediate value theorem. Again, see theorem of section 1.5. Now there are many things that need to be explained about this part, starting from since. What have we done here? We have done here something that unfortunately we have so far never seen, and it's there much later in the book. It's a tool that is very useful. It is often used in calculus to decide about things that look like this. Okay, now I can say roughly what we have done, and it's not very difficult to roughly understand the meaning of this part. Let us first see one thing. How the graph of this function f plus g looks. this is 1, this is 1 over 2, and this is 1 over 2, this is 1, so that means this is 1 over 2. Okay, this line is y equal to 1 over 2. The graph of our function, that is this y equal to x plus square root of x minus 1 looks like this. Wait, have I made a mistake here somewhere? Because the graph, no, okay, I made a mistake. The graph will not start from here but from here. Yes, it will look like this. Okay, so this is our 0.5 and this is 1. So you see that this is the domain of the function, right? 1 comma infinity. So our domain is this ray 1 comma infinity. We can only take the outputs from here. The smallest possible output is 1. Now, why have I written 1 by 2 here? I think this will also be 1, no? There is no need to consider 1 by 2. Okay, now it is okay. The shape of the graph is like this. I have already seen it in that site where we can generate graphs if equation is given. So now this is our place from where we can consider our input. So the smallest input is 1. Now when we put x equal to 1, we get y equal to 1 because this becomes 0. So when x is 1, y is 1. 1 comma 1 is a point on the graph. When x is greater than 1, y also becomes greater than 1. We have already seen those things here, you see. X plus square root of x minus 1 is greater than or equal to 1. That is the case because when our inputs are coming from here, if you look at the outputs, all the outputs are here. These are the corresponding outputs. For this input, this is the output. For this input, this is the output. So all the outputs are greater than or equal to 1. So the range of this function is the shadow of this graph if one shines a flashlight from this side, this shadow on the y-axis. Okay, now in this part we have been able to say that because all the outputs are greater than or equal to 1, the shadow lies in this region. That is, it will not come below this line y equal to 1. So the shadow is going to lie either a part of the shadow either lies on the line y equal to 1, namely this particular value y equal to 1 that we get for the input x equal to 1, and the other outputs lie above this line. That is expressed in this inclusion relation. But is this shadow equal to this? For that, if we arbitrarily choose a y1, say we have chosen a y1 here, above 1, more than 1 or equal to 1. If y1 is here, then we know from where this shadow is coming. This is our x1. If y1 is equal to 1, then x1 is 1. So now we are assuming y1 is here somewhere. Okay. Now look at this inequality. Since y1 is greater than 1, so that means you draw a line parallel to the x-axis. That line will intersect the graph somewhere. Then from that somewhere you draw a perpendicular on the x-axis. So this is your x1, and that x1 we have written here. Now from the geometry of this situation, you can see that whatever your y1 is here, correspondingly you will get some input x1 for which y1 is the output. But the problem is that is coming from geometry. Now, do you see that this entire thing rests on one assumption, namely whatever our y1 is, we are assuming that if we draw a line parallel to the x-axis, the line will intersect the graph somewhere. That is the assumption. This assumption is of course true for this graph, but do you see why it is true? It is true because the graph is not broken anywhere. It is in one piece. It's a continuous line. So that's why when we draw something, no matter where our y1 lies, when we draw a horizontal line passing through y1, it will intersect the graph somewhere. And when we drop a perpendicular from that somewhere, we get our input. So every point in this region of the y-axis appears as the shadow or appears as the output, and hence every point here will also belong to the range. But there is a theorem that helps us do these things, and that is known as the intermediate value theorem. It says that if a function is continuous, we don't know what continuity of a function is, we will see afterwards, but roughly continuity says that when you draw the graph of a function, the graph is not broken. We have seen broken graphs, Do you recall partly defined functions, particularly this function whose value is say 1 at x greater than or equal to 0 and minus 1 at x less than 0. If you draw the graph of this function, you will get two lines. To the right of x-axis, you get the line y equal to 1, and to the left, to the right of y-axis, you get the line y equal to 1, and to the left of y-axis, you get the line y equal to minus 1. So at 0, the graph is broken into two parts. So if that kind of thing happened here, say for example, if this graph was broken into two parts, then you could not have said that for any y, such a horizontal line will cross the graph somewhere. So had that been the case, you would not have found an input for every output, for every point. So every point in this region would have failed to be an output. There would have been some such points. That is not the case here because of continuity. And intermediate value theorem is the thing that assures us that such an x1 always can be found. This is the issue of this solution. The question is, why has the author chosen such an exercise that needs something so advanced that we are still far away from it? I think this is the answer. Although this is the rigorous way of solving this exercise, but I think the author does not intend for this type of solution. Instead, what the author does is this. He expects us, or actually there are two authors, right, Thomas and Finney. They expect us to draw the graph, and from the graph itself they expect us to see what the shadow is or what the output is. So this many things need not be there in the solution. You should draw the graph, because otherwise, you see, in the text itself one such example would have been worked out, in which the author at least would have said these things. It is not nowhere. The examples where ranges have been given, they are also just simply mentioned. So because of that, I think such a solution is not needed. There is no problem with finding the range of G. The way we found the range of G, there also we found the range of G without drawing any graph, but only algebra was enough. We found that we can take the point y square plus 1. For that, we get y as the output. However, in general, that is not always the case. You can think of that type of technique to find the x1 that you are seeking. What you have to do is this. You have to solve this equation for x1 in terms of y1, because when we found the range of G, there also we solved this equation, right? Sometimes solving this equation for x in terms of y is easy, as is this case. However, in other cases it's not so easy, and sometimes it will become extremely difficult, and that extremely difficult case I think occurs when we try to find the range of f dot g. So instead, Okay, so what is the ultimate conclusion of this entire thing? The conclusion is that I will write this type of solution using intermediate value theorem. That will be a rigorous solution, but you need not follow this. Instead, you just draw the graph, and from the shadow of the graph on the y-axis, you say that from the graph we see, from the graph of the function we see that the range is this. That's all. There is no point in trying to understand the intermediate value theorem and its use now itself prematurely, because that's not how things should proceed. I mean, we should only take one step at a time. We should not go ahead of ourselves. So like that, okay, but then if there is no need for you to follow this part, then there is no need to write them down also. I mean, what will I do with them now, or what shall we do with them now? So instead, what I suggest is this. This, however, we have shown. So what do we get from here? So y1 belongs to the range of f plus g. Hence, our closed ray or interval also is contained in the range of f plus g. Hence, combining this inclusion and this inclusion, we get our desired range. But for the range of this, you proceed like this. You draw the graph of the function . And domain still continues to be 1 comma infinity, but in this case, if you draw the graph, you will see that the graph looks like this. This is the point 1. So domain is still 1 comma infinity, but now the shadow of the graph on the y-axis is 0 comma infinity if one flashes light from this side. No need to write those things, okay? Flashing light from that side, those things have no meaning in mathematics. They are just said for the sake of our understanding. You just simply write like this. From the graph of the function y equal to fg x, which is x times square root of x minus 1, we see that the range of f dot g x, or rather the range of f dot g is 0 comma infinity. Okay, that will be enough. So no need to go to those advanced parts using intermediate value theorem. Those advanced parts are very interesting, but there is time for that. This is not the time. Okay, so that is 39, 40. Clearly, domain of f, x plus 1 should be non-negative, so that means x should be greater than or equal to minus 1. So this is the domain of f, domain of G. Here x should be greater than or equal to 1. Range of f and range of G will be both equal to the set of non-negative real numbers. See the solution to the previous exercise. Okay. Also, domain of f plus g equal to domain of f dot g is equal to the intersection this one is the smaller, this is a subset of this, so this is the domain of sum and product. So now the solutions have become extremely easy. From the graphs of okay, one can in fact decide what the range is from the graph, I mean the boundaries of the range. In this case, y is equal to, one boundary will have root 2, that the range of f plus g is this, square root of 2 comma infinity, and the range of f dot g is 0 comma infinity. Oh, so that means there was in fact no need to go through that much trouble from the beginning itself. In exercises 41 and 42, find the domains and ranges of f g f by g. Also now we have quotients and g by f. F of x is 2 and g of x is x square plus 1. To save time, I will just simply write the things. You write the explanations and whatever argument you need to write. Domain of f, we can put any x here. So domain of f is the set of real numbers. Range of f in this case has only 1.2 because that is the only output. Domain of g is also the entire set of real numbers, and range of g for any x square plus 1 is always greater than or equal to 1. That's because x square is greater than or equal to 0. So the range is 1 comma infinity. This again, either you can approach algebraically to show that this set is equal to this set, or you can cut corners. You can say from the graph of this function we see that this is the range. The advice is that you should write something. I mean, if it is possible to show that these two inclusion relations are true, in our usual way that avoids intermediate value theorem, then please show that and then write this is equal to this. Otherwise, if you feel that our usual calculations are not enough to handle the case and we need that advanced part, then you write from the graph of the function we see that the range is this. Okay, then we come to the quotients. The domain of f by g is R, because f by g, the formula looks like this. Here you can put any real number x, you will get an output. So the domain is R. What is range of f by g? Range of f by g turns out to be equal to 0,2. Again, you can either find it algebraically or you can find it geometrically from the graph. Domain of g by f, just like f by g is R, and range of G by F is going to be, it will be the reciprocal, no? So range will be unbounded 1 by 2 comma infinity. (42) (1 plus square root of x). F is again a constant function, so domain is the entire set of real numbers. Range is the singleton set with the only element 1. Domain of G. Negative x's are not allowed because of that square root, so non-negative real numbers. Range of G, I think, will be 1 comma infinity. Yes. Because 1 is the least possible value, then for other values of x, if you put x equal to 0, you get 1. For other positive values of x, you get values greater than 1. Okay, then domain of f by g is the same as the domain of g by f. And these domains are also equal to 0 comma infinity because of the presence of this. Range of f by g turns out to be the half of an interval 0 comma 1, and the range of G by f is the unbounded interval 1 comma infinity. After this we have composition of functions, but I think it's better to continue in the next video. We could have started the composition here itself, but I did not know that we were in fact going to decide to abandon that intermediate value theorem approach. So now our decision is this: if the problem is solvable using ordinary calculations, then we will write such a solution. Otherwise, we will have to cut corners. There is no other way. We have to take the help of the graph of the function and say that the range is this. So that will be all for today. If you want, you can write something in the comment section if you have any doubt regarding these things. That is, tomorrow we have analysis, real analysis, and after completing real analysis, I mean at least the single variable case, I think it will be better. Of course, we will also go to the multivariable case, that is analysis 2 by Terence. but I think then it will be better to alternately do real analysis and complex analysis, because that thing is also there, that is very important. Anyway, so see you tomorrow. So until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.